Hello everyone, welcome to Sweetie Speaks official YouTube channel. Today's topic is career opportunities in Frontend VLSI. In the previous lectures in this series, Getting Started in VLSI, we had seen first about various VLSI domains. Then we got a gist of what are various career opportunities in VLSI. Now we will deep dive into particularly front-end VLSI career opportunities so that you get a better understanding of what is the kind of work in job roles in front-end VLSI. If you can notice, we are going gradually. In order to understand what are various VLSI job opportunities, you should first understand VLSI design flow. Then we got a gist of what are various job opportunities in different domains. It can be front end, back end, then it can be analog, digital, mixed. And now gradually we are moving to in depth of what each job role does. Why we are going gradually? So that you get a better understanding if we go stepwise and you can make a better decision on what career in VLSI you want to have. Let's get started. Just an overview, what are different career opportunities in front-end VLSI? We had seen this in career opportunities in VLSI. So first one is architect, a person who designs architecture. Then RTL designer, who will actually code your design using the hardware description language like System Verilog. We have CAD or EDA engineers who work on creating the tools which various people like RTL designer and verification engineers use. Now there is design verification in which we actually verify the functioning of the design and ensure that it is working properly. It can take various forms like verification engineer. Now verification engineer can work on IP subsystem, SoC, CPU. Then we have emulation engineer. They will work on emulators. We'll see in detail what are like in depth we are going to see each job role. For now, just remember these are the ones. Then we have FPGA engineer who works on FPGA. We have formal verification engineer who will do formal verification. Now let's go in depth of each of these job roles to understand what these people do. Let's understand what architect does. Architect will first understand the design requirement. Now you will have a lot of customers asking for a particular chip with particular specifications. The architect first needs to understand these design requirements from the customers so that they can design the architect accordingly. After understanding this thoroughly, they'll develop a architecture. Once the architecture is developed, they need to create a documentation. We call it as architecture specification. They architect all the digital blocks. The design is micro architected, not coded, just micro architected. After this, they collaborate with RTL designers for actual implementation of the design. So designers might have lot of doubts. Since architects are very senior people in industry, they help the designers to properly understand this design requirements and what is the right way to design a particular design. So this way, architects play a role in VLSI industry. Then they also need to provide technical support to the customers, like whoever are their customers. First they understood the design requirement, right? Now once the design is implemented, you provide them the chips. It is possible they need technical support. Now since architects are very highly experienced people, they are the right people to understand what issues customer are facing or what are their queries and resolve them. The next job role was RTL designer. They do the actual development of the design using hardware description language like System Verilog. They will design, develop, and test the RTL. Now, in VLSI industry, some very important thing which you should remember is PPA. What is PPA? Is power performance area. Everyone wants a chip which performs good, which consumes less power, and which has less area. Now, see, there is always a compromise. If I want more performance, of course, I will need to give more power, and the chip might be complex, it will take more area. Arriving at the very optimal number of this power performance area is a very critical job, and it is a uh, very crucial job which designers need to perform. You need to optimize your design in terms of power, performance, and area. Now they will also do something called as linting and CDC. What is lint? In lint, we analyze the hardware description level code, whatever we wrote in system Verilog, to identify potential design issues and coding violations so that I can correct it right away. Then they have something called as CDC, which is clock domain crossing. In this, they use tools to read the RTL source files, check for missing or inadequate synchronization logic, and fix them. Then they perform something called as synthesis. In synthesis, your RTL code, which is written in system Verilog, is converted into gate level netlist, because this gate level netlist is the input which we need to give to physical designers. Physical designers are people who work on backend. They will collaborate with verification engineers, emulation engineers, PD engineers to debug the design. In case there is any bug found in the design by verification engineer, emulation, or physical design engineer, they'll debug it with them if required, and they need to fix the bug, tell them to test it again, and ensure that your design is finally fixed. These are the job roles of RTL designer. Now, before we understand what is design verification job role, let us see what are different levels of verification. The first level is IP, which is called as intellectual property. Say I design a very good memory, very efficient memory, and I want to make it as intellectual property. It is my intellectual property. Now, I can sell this intellectual property to different vendors. Intellectual property is a logic circuit or a design that can be used by multiple vendors in different chips, which will be used for different purposes. So, whoever wants to use your IP, they will pay you for that. Subsystems. Subsystems are a combination of your pre-verified IP, which is intellectual property, and in case your chip needs a specific new IP, which is specific to your chip. So you combine the pre-verified IPs which you might purchase from someone and your new designed IPs into subsystem. Now, SoC is a combination of multiple subsystems. We call it system on chip. System on chip is IC that compresses all of the system's required components into a single piece of silicon. Like AI chips, they are very complex. They'll have all different kinds of subsystems which are required to run your AI. These complex chips are called a system on chip. Then we have CPU, which is central processing unit. Now, in central processing unit, it is one of the very critical form of verification. Why? Because you need to check for instruction set architecture of your processor. Now you need to understand that CPU will have a lot of programming and a lot of operating modes. That is why the CPU verification is one of the most challenging kind of verification. Then we have GPUs, which is graphics processing unit. What is the challenge in verifying GPUs is you need to create a lot of efficient data parallel algorithm, because GPU will analyze a large amount of data, and you need to ensure that it analyzes in parallel, or you need to restructure the existing sequential algorithm so that the processing is faster. ASIC stands for Application Specific Integrated Circuit. These are chips which are designed only for certain application. For example, chips which will go in your smartwatch, they can't be used for any other purpose, say embedded, like embedded equipments in gym. I can't use the chips which are in the smartwatch for gym equipments. It is only designed for smartwatch. These kind of chips are called as application specific integrated circuit. Now, people who work on these different levels of verification are called as verification engineer. It can be IP verification engineer, SOC verification engineer, GPU verification engineer, ASIC verification engineer. If you start searching verification engineer jobs, these are different job roles which you will see. Let us see what verification engineers do. They work with designers too. First, they need to understand the design, then debug the failures, get the bug fixes from the designers. Now, in verification, one of the key skills which is used nowadays is called as UVM, which is Universal Verification Methodology. Verification engineers will create the UVM test bench which is particular to your design. When you go through UVM, you will understand what UVM is, how it works, what is UVM test bench, what are different components. So this is a completely different subject. It's a complete different skill that you need to have as a verification engineer. They need to write the test cases to verify that the design is correct. Verification engineers also write coverage to ensure that we test the design thoroughly. Designs are very complex nowadays. How will I ensure that I cover the entire code? There is something called as code coverage. These coverage concepts are a part of system verilog. System verilog is another skill which verification engineers need to have. When you read system verilog, you will also come across a concept called as coverage. And there are different types of coverage. Like I just gave an example of code coverage, which tells you how much code of the design you are covering. Like this, there is a functional coverage which tells you how much functionality of design you are covering. So this is just a complete chapter in system verilog coverage. Verification engineers need to verify that the design is functionally correct. It means they verify the design for functional correctness. They need to ensure that there are no bugs in the design. There are new techniques which are coming up in verification called as low power verification is one example. In this, what we do, we reduce the individual components of power as much as possible. See, when your processor is running in low power, there is no need to keep all the various components inside your design on. You can switch off some components. The performance will reduce in low power, that is fine, but it is important that your chip consumes low power, and it just ensures that the applications which are required to run at that time, only those run, and what digital circuits are not being used, they can be switched off, and still your chip should be able to perform the functionality as expected. Such kind of testing is done in a technique called as low power verification. What does emulation engineer do? In emulation, we mimic the behavior of design using emulators. Then we will run the test on emulators to ensure that there is a correct design behavior. We already have simulation, then why do I need emulation? First thing is emulation is almost 100 times faster than simulation. So sometimes there are very complex chips, and it takes a lot of time to run these test cases in simulation. At that time, it is possible to run certain things in your emulation. And since it is faster, it is good for SoC, system on chip level kind of verification. Emulator provide you excellent debugging capability. Debugging becomes very easy. If you try to go through emulation in detail, you will understand how and why they have excellent debug capabilities. For now, just we are trying to understand what does emulation engineer do. That's why we are just seeing an overview. What are disadvantages of emulation? Emulators are very costly compared to simulators. This is one of the disadvantages. And in emulation, we don't have so much visibility to internal signals. That is why if you want to perform a verification for a small block or a small IP, this emulation is not suitable because you don't have access to so much internal signals, and IP you need to verify thoroughly. That is why you can't use emulation for like block and IP kind of verification, but it is excellent for SOC verification because it is very fast and it will run your SOC tests very fast compared to simulators. That is why emulation is also used for testing some complex SOCs. Now, what is FPGA engineer? They will mimic the behavior of design using FPGA, and then they will run the test on FPGA to ensure that your design is behaving correctly. Why do I need FPGA? I have simulation, I have emulation. Why am I using FPGA? First thing is FPGA stands for Field Programmable Gate Array. It is easily programmable. If you want to change the functionality of the design, you can easily program it on FPGA, change the functionality, and see if this one is better or that one is better. That kind of thing also you can do. It is more accurate and reliable compared to simulation, because in FPGA you are actually creating a hardware inside your FPGA, which means the hardware is actually mimicked in a real time hardware circuit which is inside your FPGA. That is why this hardware will be definitely more reliable than simulation. In simulation, we just have software kind of models, we don't have any hardware. That is why it is more accurate. What are advantages of FPGA? First thing is FPGA can allow you to run multiple chips in parallel. FPGAs are more accurate than emulators also. These are some of the advantages. What are disadvantages? If you remember, in emulation we told that they have excellent debug capability. FPGAs have less debug capability compared to emulators. Let's see what is formal verification. See, formal verification is like a new technique which industry is adopting now because they have realized what are the benefits of formal verification. It can take various forms. Let us see one by one. First thing which you can do in formal verification is connectivity. Now, SOCs are getting very complex. There are thousands of connections in your SOCs. Writing UVM tests to verify each of these connections is very hectic job, and it does not give so much return on investment. Like so much time which you spend on coding this, you don't get so much benefit. So what we do is there is a technique called as connectivity verification in formal. In this, you can easily check the thousands of connectivity between SOC, and you don't need to write any UVM test bench in formal. This is like one of the biggest advantage. We don't have any UVM in formal. You just use the connectivity tools, and you tell that this is the source signal, this is the destination signal, I am expecting them to be connected, and the tool will tell you whether these are actually connected or they are not connected. It is that simple. The second thing which we use is FPV, which is formal property verification. In this, we use system verilog assertions to test the design behavior. One simple example, say my design spec says whenever I have a request, I should get acknowledgement within 3 clock cycles. To test this thing, I will create a simple assertions which will tell that I got a request signal. After that, I'll wait for 3 clock cycles and see if if the acknowledgement was high after getting the request in 3 cycles. Uh, so these kind of things can be easily tested in formal property verification. What are advantages of formal? You don't need to create a UVM test bench. So as soon as you get your design, you can start writing assertions, start doing connectivity. It is like you get the design, same day you can start working on formal and find the bugs. Whereas simulation will take time to bring up the UVM test bench and all. Meanwhile, you can easily find the design bugs and get them fixed, because debugging at SOC level is very complicated, and if you debug and you just find that there is some basic error, it costs a lot of time and effort. To minimize this time and effort, we can use formal property verification. Another thing which we can do in formal is equivalence checking. Now, say I am expecting the two designs to be functionally correct. Only some aspects, say power, is different in the two design, but the functionality wise they should be same. These these kind of checking is called as equivalence checking. What equivalence checking will do? It will take two designs and it will try to find out the functional differences between them. Ideally, there should be no functional differences. If there are some functional differences, it will be reported, and then we can fix the design and then again recheck the equivalence, and until you get the functionality exactly as it is, we will keep on repeating this. Then in formal also, now the formal tools are supporting the low power verification. So at IP level you can easily do low power verification, because see, if you start doing it in simulation and all that, it takes a lot of time to bring up your environment and all. In formal verification it is very quick. Now there are certain things which can be easily verified using formal, like FSM, arbiter. See, for arbiter, there is something which we need to verify. We call it as fairness. If the arbiter is being shared, say, by two masters, and I'm expecting that it should be round robin. So, to ensure that it is properly round robin, I will use formal verification. It is very easy to test arbiters in formal verification. When you understand formal verification in detail, you will know why it is more easier to do these kind of testings in formal. And even FSM. FSM means there is a state. Then, if this is the particular thing, then it moves to stage two. If there is another thing, then it will move to stage 3. These kind of things also can be very easily verified in your formal verification. Another thing which you need to understand about formal is your tool itself generates all possible inputs. So it is a thorough testing. In simulation, we program the inputs. It doesn't generate all possible inputs. We tell that what kind of inputs we need to generate. So it is possible that in formal verification you will get some design scenarios which you have not even imagined in your simulation, and such kind of things help you find design bugs which you don't even expect, like you can't even imagine. These kind of things are also easily detectable in formal verification. It is a very, very powerful technique. What are advantages of formal verification? It is more rigorous. As I said, the tool will generate all possible scenarios. So it can find the bugs which your functional verification will miss. What are disadvantages? It is more complex and time consuming. Why more complex? Because see, there are a lot of different kind of inputs, and in some cases, like in some complex design, we in formal, one problem is there which we call as convergence. So convergence means, are you able to generate all possible inputs? Sometimes the possible input combination is so high that it becomes very difficult to converge it. That is called as a convergence problem. In that cases, we decide that what are the kind of inputs we want. We try to minimize the kind of inputs, or we try to sign off with the designer that these many different scenarios we have generated, is this enough or shall we generate more? So these kind of things we need to do in formal, which is little bit more complex and time consuming. Was about formal verification. Let us see what a CAD or EDA engineer does. There are a lot of tools which we need to use in VLSI. Like if you see in formal, the most widely tool nowadays is Jasper Gold. Then if you want to see in simulation, we are using Verdi. There needs to be someone who will design these tools. What so your CAD or EDA engineers do this thing. They design and develop your EDA tools. They ensure that the tool will support all language syntax. For example, I am using formal tool Jasper Gold. I want to write assertions. Assertions I write using System Verilog assertions. So there is a language reference manual for System Verilog. We call it as System Verilog LRM. It will give you in detail what are the different kind of syntax which should be supported for assertions. Your EDA engineer needs to ensure that all these syntax are being supported by the tool. Then they need to test the tool thoroughly. If there are any bugs or there are certain syntaxes which are not supported, they need to fix the design of the EDA tool so that it supports everything. Until it supports everything and it is complete, they will keep on repeating this. They will test it and they will again correct the design and ensure that all the syntax are being met. And they also need to support the vendors who are using their tool. This is what a CAD engineer does. Now, I hope that you are able to understand which are different career opportunities in VLSI, and specifically in front end. This will help you make a better career choice and a better decision, because now you know what are various job functions and what we expect in each of them. Best luck for choosing a career in VLSI. To stay tuned to such technical content, please subscribe to Sweetie Speaks official YouTube channel. Thank you.